Good morning. We'll continue our discussion on slope stability analysis. For a couple of videos, we have been discussing a few methods. It included phi zero analysis, and in the previous video, we had discussed the Swedish circle method of analysis wherein C5 soils can be analyzed. In this particular method, the friction circle method, again, the failure surface is assumed to be an arc of a circle. We'll take the same slope ADB and we'll take the same arc length L. So ADB is a slope and AB, the curve, is a failure surface, a probable failure surface whose length is L along the curve. And since it's part of a circle, it'll obviously have a radius R and it'll be part of a circle whose center is O. So three forces acts on the system. Number one is a self-weight W of the soil, which means that ADB, this portion, is a failure mass. That failure mass will have a mass or a weight, to be specific, which acts through the centroid or center of gravity of this geometry. Assume that we are talking about 1 unit perpendicular to the screen that you see. So the volume of soil involved in this area multiplied by 1 unit is the one that we are interested in, and it'll have a weight, let's say capital W, acting through the centroid. The second force is a cohesive strength C of soil acting along the slip surface. The slip surface is AB, which is curved, and at each point of the slip surface the cohesive strength will get mobilized. So the nature of the cohesive strength is like this direction because the tendency of the failure mass is to move downward and outward. So cohesive strength tries to keep it in the other direction and it'll be opposite to the direction of downward and outward movement. Third force is a reaction on the slip surface. Just like any other reaction, due to any body on a surface, the reaction is perpendicular to that particular plane, and since this is a curve, the reaction will have unique directions on each of the points on the curve. So anyways, you have three forces for us to analyze the system. Number one is a weight of the soil W acting through the centroid. Number two is a cohesive strength which acts along the slip surface and it'll have unique directions in all the points that we are concerned. And the third one is a reaction force on the slip surface. Again, that will have a unique direction as well. The reaction force R on the slip surface will be at an angle phi to the normal at the surface, which means a combined normal force and the frictional reaction force. To simply put in geometry, you have the surface here and it'll have a normal here, and with respect to the normal, the reaction R will be inclined at phi, where phi is the angle of internal friction. Now this normal and this direction of R is concerned with just this point. As the slope of the slip surface changes, at each point the normal to the surface also changes. So the normal at any other point will have another direction likewise. Hence the direction of reaction R also changes at each point along the slip surface AB. So when you take the total slip surface AB, each point on the slip surface will have a unique normal to it because the slope changes at each point, and for the same reason each point will have a unique direction of reaction R. So let's take this case where the reaction R is like this, and when you have another point like this, the reaction R will be like this. Likewise, you'll have n number of reactional directions at each point along the slip surface AB. So if the lines of each reactions are extended, they'll be tangential to a circle with center O and radius R sine phi. Now this R sine phi is explained in the previous video of Swedish circle method, how you get R multiplied by sine phi. So such a circle is called as a friction circle. If the lines of these reaction forces are extended, they'll be tangential to a circle, which is a friction circle, and that circle will have a center O and a radius r sine phi. And for purely clay soil, the frictional circle reduces to a dot because you don't have phi, so sine phi turns out to be 0 and r sine phi turns out to be 0, which means that you don't have a circle, you just have a point. Or every reaction will pass through the center of the circle when it's pure clay. And if it's not pure clay, you'll have a circle like this. So this circle with the red line is what we call as a friction circle, whose center is O and the radius is r sine phi. And the three forces that we discussed, W, R and C, form a force vector as shown below. So W is here, the weight that passes through the centroid, R is here, the reaction, and C is here, the cohesive force. So all these three forces, when put together, forms a force vector triangle as shown below in this figure. And the process is to assume a slip surface AB whose weight W can be obtained and reaction R is calculated. And from this force vector triangle, knowing the reaction R and weight W, the cohesion C, which is mobilized, can be found out. And likewise, you get any other slip surface iterative process, ADB dash or ADB double dash, etc., and you proceed with finding weight W, reaction R, and hence cohesion C, mobilized C. And you can play around with different combinations of the slope failure geometries, and the slip surface which gives the least factor of safety is considered to be critical. Just like in the previous example that we discussed in Swedish circle method, you'll take ADB and let's assume that you get a factor of safety of 2, and the next iteration will have ADB dash, where B is somewhere here, and the factor of safety that you get would probably be, let's say, 1.5, and the next iteration you take would be ADB double dash, where you get a factor of safety of 1.1, and finally you consider the factor of safety 1.1, the least value, and that slip surface which corresponds to the least factor of safety is considered to be critical, which means as an engineer you are targeting that slip surface and you need to reinforce that slip surface. That's the whole idea of slope stability analysis using friction circle method. The next method is Taylor's stability number and charts. A stability number defined by Taylor is Sn equal to C by Fc, factor of safety for cohesion, multiplied by gamma, unit weight, and h, the slope height. So a figure is shown here where slope height h is marked, and this berm, the base width, is n multiplied by h, and the total depth of the failure surface, the slip surface, is df multiplied by h. So based on which he formulated this equation or relation, stability number, where C is a cohesion, Fc is a factor of safety, h is a slope height, and gamma is a unit weight of soil. And you can have different geometries of slopes like this, angle varying, depth varying, etc., etc. And Taylor determined the values of Sn for finite slopes analytically and presented as charts and tables. So he made our job easy by considering different geometries and arriving at the finite slopes failure and hence the stability number Sn, and presented the data, the populated data, as charts and tables. So we can obtain stability number corresponding to the values of slopes, angle I, and angle of friction phi. So that is a concept of Taylor's stability number and stability chart. And to know more about the stability number and charts, I would suggest you to refer to page 453 of the soil mechanics textbook by author K.R. Arora. And in case you are interested to score marks in exam, and you can have the chart provided for the examinations. So no one expects you to by heart the Taylor stability numbers based on different geometry. And the idea is quite simple. Taylor determined the values for different geometries, and we can obtain the stability number corresponding to the values of the slope angle I and the angle of friction phi.